Unit 5, pages 156 to 160. Particle motion problems. Particle motion problems deal with particles that are moving along the x or y axis. Thus, we are speaking of horizontal and vertical movement. The position, velocity, or acceleration of a particle's motion are defined by functions, but the particle does not move along the graph of the function. It moves along an axis. Most of the time, we speak of movement along the x-axis. In Units 6 and 7, particle motion is revisited, and at that time we will deal more with vertical motion. For the time being, will focus on horizontal motion of particles. In this lesson, we develop the ideas of velocity and acceleration in terms of position. We will speak of two types of velocities and accelerations. So first, let's define average and instantaneous velocity in this box. So, average and instantaneous velocity are both the rate of change in position. Okay, so the average velocity on an interval AB is equal to position of A minus position of B all over A minus B. And instantaneous velocity is equal to the derivative of the position at some value C. Okay, so P of T equal to our position function. Right, so instantaneous velocity is the derivative of the position. So we'll also call that V of T. And average velocity is the same thing as taking the average rate of change of position. So a particle's position is given by the function P of T equals e to the t sine t, where P of T is measured in centimeters and t is measured in seconds. What is the average velocity on the interval 1 to 3? Our average velocity is going to be P of 1 minus P of 3 all over 1 minus 3. Plug that into a calculator, I get negative 0.547 over negative 2, which is equal to 0.274 centimeters per second. All right, and then the instantaneous velocity of the particle at time 1.5, we need the derivative. So to take P prime of T, we have to use product rule. So our first function is e to the t, derivative of e to the t is e to the t times the derivative of t, which is 1 sine t, plus e to the t, and the derivative of sine is cosine. So P prime of t is equal to e to the t sine t plus e to the t cosine t. And since I want time equaling to 1.5, P prime of 1.5 is equal to e to the 1.5 sine 1.5 plus e to the 1.5 cosine 1.5. So the instantaneous velocity of the particle at time 1.5 seconds is equal to 4.787 centimeters per second. All right. So before we proceed, a connection must be made. When given a function f of x, how did we find the slope of the secant line on the interval from x equals a to x equals b? So the slope of secant was equal to f of a minus f of b all over a minus b, right? And this looks very familiar to our average velocity equation, which is equal to E of a minus P of b all over a minus b. And that was the average velocity on the interval a, b. Right, so the average velocity on an interval is equal to the slope of the secant. And if we look even closer, instantaneous velocity is equal to e prime of c, which is the slope of the tangent. All right, so now let's look at average and instantaneous acceleration, which is going to be the rate of change in velocity. So our average acceleration on the closed interval AB is equal to V of A minus V of B all over A minus B, where V of t is equal to the derivative of position. Remember, velocity is equal to the derivative of the position function. So the instantaneous acceleration is equal to V prime of c. Or another way we could say it is the second derivative of our position function, p double prime of c. A particle's position is given by the function e to the t sine t, where p of t is measured in centimeters and t is measured in seconds. What is the average acceleration on the interval t equals 1 to t equals 3? So in the previous page, we found that e prime of t is equal to e to the t sine t plus e to the t cosine t. And p prime of t is v of t. So average acceleration is equal to v of 1 minus v of 3 over 1 minus 3. So I'm plugging in 1 and 3 into this equation, and we get negative 10.403 centimeters per second squared. In the instantaneous acceleration, if v of t is equal to e to the t sine t plus e to the t cosine t, v prime of 1.5 will be equal to acceleration, instantaneous acceleration at 1.5. And when I plug that into a calculator, I get 0.634 centimeters per second squared. Okay. So on the next page, we kind of summarize what we've learned from the derivative and second derivative in the original function and comparing it to position, velocity, and acceleration. So we know that f of x is our original function, and that corresponds with the position of the particle. F prime of x is always our first derivative, and that corresponds with the velocity of the particle. And f double prime of x is equal to the second derivative, which corresponds to acceleration of the particle. And velocity and acceleration will help us to determine the speed of the particle. Right? So using the relationships that we know between f prime, and f double prime, we're going to summarize some of the relationships between position, velocity, and acceleration. So velocity being the derivative, and position being our original function. Right? If velocity is 0 or undefined, that means that our position has a potential turnaround value, turnaround point. Right, so this is our critical values, and they correspond to potential turnaround points of our particle. If our velocity is greater than 0, then our position, the motion of our particle, is increasing. If our velocity is less than 0, then our particle is decreasing. And when we say increasing, we mean going forward. And by decreasing, that means going backwards, or going back to where it started. And if we are changing from positive to negative in our velocity, then our particle has changed positions, or changed positions, and is going backwards. And if we're changing from negative to positive, then our particle has changed positions and is going forward. Now with acceleration, our second derivative, and velocity, which is our first derivative, if acceleration is 0 or undefined, then velocity has a potential change in velocity. And if acceleration is greater than 0, then velocity is increasing. If our acceleration is less than 0, then our velocity is decreasing. And if our acceleration changes from positive to negative, then our acceleration is changing from increasing to decreasing, and vice versa if it changes from negative to positive. All right. So these here still represent points of inflection on f of x, or our position. Okay. So if we look at this graph, it represents the position s of t of a particle which is moving along the x-axis. So if we're looking for points when the velocity is equal to 0, velocity again is f prime of x. When that is equal to 0, those are our horizontal tangents. Right? So v of t equals 0 at b and d. because S of t has horizontal tangents at those values, at those points. Okay. So at what point does the acceleration equal 0? So the acceleration equals 0 in between those horizontal tangents. So if our horizontal tangents are B and D, then right in between that, at point C, we will have our acceleration equaling to 0, right? Because we're changing concavity. We went from concave down to concave up. So A of t equals 0 at C because S of t has a point of inflection. On what intervals is the particle's velocity positive? So velocity, once again, is our derivative, and our derivative is positive when our function is increasing. So our function is increasing in this section here and this section here. So v of t is greater than 0 on the interval from, say, 0 to b. Since that goes on forever, let's just say negative infinity to b, and d to infinity, because S of t is increasing. And the particle's velocity is negative right in this middle section here because our function is decreasing. So v of t is less than 0 from b to d because S of t is decreasing. Okay. Now we're looking at acceleration, positive and negative, right? Acceleration is the second derivative. When the second derivative is positive, we are concave up. So we are concave up from C on, right? So here's our point of inflection where we change concavity. So from C on, we are concave up. So A of t is greater than 0 on C to infinity because S of t is concave up. And negative acceleration occurs when we're concave down, which is from negative infinity to C. So A of t is less than 0 from negative infinity to C because S of t is concave down. Alrighty. So there are 5 rules or commandments of particle motion when we're talking about particles that move along. So this is specifically for particles moving along the x-axis. Okay, so the 5 rules are: if B of t is positive, the particle is moving to the right. if v of t is negative, the particle is moving to the left. Speed is increasing when v of t and a of t have the same sign. Okay, so if they're both positive or if they're both negative, the speed is increasing. Speed is decreasing when v of t and a of t have opposite signs. So if velocity is positive and acceleration is negative, we're decreasing in speed. Velocity is positive and if velocity is negative and acceleration is positive, we have decreasing speed. And then last but not least, if v of t equals 0 and a of t does not equal 0, the particle is momentarily stopped and changing directions. Okay, so if the velocity is 0 but the acceleration is not 0, then the particle is momentarily stopped and changing directions. So suppose the velocity of a particle is given by the function v of t equals the quantity t plus 2 times the quantity t plus 4 squared, for t being greater than or equal to 0, where t is measured in minutes and v of t is measured in inches per minute. Find the values of v of t and v prime of 3. Based on these values, describe the speed of the particle at time t. So v of 3 is equal to 3 plus 2 times 3 plus 4 squared, which is equal to 5 times 49, which is 245 inches per minute. So since that's positive, we're looking to see if the derivative of v of t is also positive, since the derivative is the same as acceleration. So the derivative, first and foremost, will be t plus 2 times, So v of t is equal to t plus 2 times t squared plus 8t plus 16. So v prime of t is equal to, if I use product rule here, I'll get 1 times t squared plus 8t plus 16 plus t plus 2 times 2t plus 8. So v prime of 3 is equal to 9 plus 24 plus 16 plus 5 times 6 plus 8, which is equal to 119 inches per minute squared. So since both of these values are positive, so since v of 3 is greater than 0 and v prime of 3, which is equal to a of 3, is greater than 0, then speed is increasing at t equals 3 because my velocity and acceleration are both the same sign. They're both positive. On what interval or intervals is the particle moving to the left or to the right? So our particle is moving to the left or to the right, depending on the sign of my velocity. So I'm going to make a sign chart for my velocity. And I know that v of t is equal to 0 at t equals -2 and t equals -4, which are not on our interval because our interval is t greater than or equal to 0. So when I make this sign chart, I know t will be on the top, v of t will be on the bottom. So my first t is 0 because that's where my function actually starts. And then there are no critical values. So if I look at this, it doesn't matter what I plug into this, as long as that number is 0 or greater, my actual velocity will always be positive. Right? I can plug in 1, I can plug in 2, I can plug in 15. It doesn't matter, my velocity will be positive. So since v of t is greater than 0 for all values of t greater than or equal to 0, the particle is always moving to the right. Okay, so there are no problems for you to work through on your own. However, I would like you to work on some of the homework problems just to familiarize yourself with this idea of particle motion.